Right, I had a request to show some of the mathematics behind what I was doing on my consumer theory handout by hand. Now, I have a video on the consumer theory handout. I'll put a link here. And I also have a video where I used the symbolic algebra program, Maple, to go through the derivations, or at least most of those derivations. But I had a request from somebody wanting to see how to go through and do at least the left-hand side of this sheet by hand. Starting with a utility function like this, a Cobb-Douglas utility function, and a generic budget equation, he wanted to see how we can derive the Marshallian demands. So x is a function of price of x, price of y, and the budget, and same thing for y. And then he wanted to see how do we take the Marshallian demands and convert them into indirect utility functions. And then he wanted to see how do we take that indirect utility function and by hand use Roy's identity to get the Marshallian demands back. Now I'm kind of tired, but I'm going to give this a try, and bear with me if I stumble or make some mistakes along the way. So let's get started. So the first thing you want to do if you are going to figure out the Marshallian demands, what we want to do is just solve this for x star and y star, the optimal amount of x and y. And there are two ways that you could go about doing this. One way would be to use a Lagrangian multiplier method. I have a video on that. See my webpage, www.berkeyacademy.com, and click on the microeconomics section. You'll be able to find it there. Just search for the word Lagrangian. I'm going to use a little bit simpler method that's an equivalent method, and I'm going to use two equations and two unknowns. And the two equations are basically to set the marginal rate of substitution. This is the way I typically will do this. Marginal rate of substitution, set that equal to the ratio of the prices, price of x over the price of y. And then the second equation is just going to be this budget line equation. And again, I have a video showing you how to get the marginal rate of substitution for a Cobb-Douglas utility function. Very simple process, but the shortcut rule is to take the exponent on the x times y, so 0.3y, divided by the exponent on the y times x in the denominator, 0.7x, and that is the marginal rate of substitution, which is just the ratio of the derivative of utility with respect to x, the partial derivative of utility with respect to y, and set that equal to the ratio of the price of x over the price of y. And what we want to do now is just solve this equation for either x or y and plug it into the budget equation and see what we can simplify. So I'll go ahead and I'll say we're going to solve this for y. So we'll say 0.3y equals the price of x over the price of y times 0.7x, and take a minute and solve that for y. I'll pause the video. Okay, I'm just going to leave it like this instead of dividing the 0.7 by the 0.3 because I think all this is going to allow us to do this a little more simply. So now that we know that y is equal to this expression, 0.7x times p of x over 0.3 times p of y, we can substitute this expression into the budget equation and for y, and then we can solve it for x. So again, I encourage you to pause the video and do this, and I'll show you the result. So what we get is this expression after plugging in this into the budget equation for y. And what's going to happen immediately is this price of y and this price of y are going to cancel. And that's all I've done between this line and the next line. Then, in order to simplify this, there are a lot of ways you could go about doing this, but what I'm going to do here between this line and the next line is just multiply everything through by 0.3 to get rid of that 0.3 out of the denominator there. So multiply the first term by 0.3, this term by 0.3 so that will cancel in the denominator, multiply the budget by 0.3, and then you get this expression, which you can see is going to be pretty easy to simplify. We have 0.3 times the price of x times x plus 0.7 times the price of x times x. So on the left-hand side, what we're going to end up with is the price of x times x. So the price of x times x equals 0.3 times the budget. Solve that for x. We call that x star. That's the Marshallian demand for x. And it's going to be 0.3b, 0.3 times the budget over the price of x. And that's how I got that Marshallian demand function on the consumer theory handout that I have. And by going through and doing exactly the same kind of thing, we could solve this for solve this for x would be one option, plug it into the budget line. Or at this point, we could take this x star and plug that into the budget line for x, and then solve that for y. You can basically plug this into any of those equations, and then you're going to get y star out. And since I've shown you how to do x star, I'll just show you the result for y star. Y star is going to be equal to 0.7 times the budget over the price of y. So those are the Marshallian demands. Now, the next thing you'll want to see is how do we take these Marshallian demands and convert them into an indirect utility function. What an indirect utility function does is take the prices of x, the price of y, and the budget, and tell us directly, even though we call it an indirect utility function, it tells us, it computes the amount of utility this person will be able to get with this budget at prices y, py, and px. So in order to get the indirect utility function, all we need to do is take these two functions and then substitute x star in here for this x, substitute y star in there for that y into the budget equation. Oh no, I'm sorry. I'm getting this backwards. We don't substitute them into the budget equation. That would give us an expenditure function. What we do is we substitute them into the utility function, because the indirect utility function is going to give us how much utility this person gets. So let's go ahead and do that, and then the difficult part is probably going to be just simplifying that. So our utility function is x to the 0.3 times y to the 0.7. So let me choose a different color here. So utility equals x to the 0.3. So what we're going to have is this 0.3b over the price of x, because that's the optimal amount of x star. And when we figure out how much utility somebody has, we're going to raise that to the 0.3 in this person's utility function. And then y raised to the 0.7, but we plug in, well, what's the optimal amount of y? 0.7b over the price of y. And now what we want to do is figure out how we can simplify this a little bit. And there are a few ways that we could go here to simplify it, but what I usually do is just leave the b and the px and the b and the py inside parentheses raised to the 0.3 and raised to the 0.7. And all I usually do is pull out the 0.3, these constants, and the 0.7, and put them out front here. So in order to pull them out of the parentheses raised to the 0.3, you're going to have to raise 0.3 to the 0.3 power. So 0.3 raised to the 0.3 gives us 0.6968 or so. So that's let me give us a color that we can actually see here. 0.6968. So that's the 0.3 to the 0.3 part. So instead of having it inside the parentheses, we're going to bring it out as a multiplier. And we're going to do the same thing with the 0.7 to the 0.7. And 0.7 raised to the 0.7 power is 0.779. So 0.779. And if we rewrite this and clean this up a little bit, that's going to give us that utility. So this is an indirect utility function because it's not a function of X and Y, it's a function of the budget and the prices. We can write it this way. 0.6968 times 0.779 is approximately 0.5428. So 0.5428. So that's just taking care of those numbers. And then we're going to leave this as B over the price of X raised to the 0.3. And here B over the price of Y to the 0.7. Now we could, if we wanted to, combine those two B's on the top there because that's going to add up to 1B, right? So an equivalent way, let me put that Y back on the P there, an equivalent way to write this would be 0.5428 B, because B to the 0.3 times B to the 0.7 is B to the first, and then we could just say divide that by price of X to the 0.3, price of Y to the 0.7. So just doing some basic rearranging there. Now, so this is our indirect utility function. One way to write it. So, now that we have our indirect utility function, the last thing I'm going to show you in this video is once we have an indirect utility function, how can we get back to the point where we have the Marshallian demands if we did not already know them. Okay, so we already know them, but if somebody just handed you an indirect utility function like this one that we just generated, how can we take that and get our Marshallian demand functions back? In order to do that, you can use something called Roy's identity. And Roy's identity says, so Roy's identity just says that if you want to get the Marshallian demand for X back, then you can take the indirect utility function, and let's just call that, okay, let's call that, say, U bar. Okay, U bar is now our symbol for an indirect utility function. Roy's identity says that if you take the derivative of U bar, this equation that we just created up here, take the partial derivative of that with respect to the price of X, and then divide that by the partial derivative of U bar, the indirect utility function, with respect to the budget, then what that will give you is the X star, that Marshallian demand for X. And similarly, if we wanted to get the Marshallian demand for Y, the only thing that would change is instead of taking the partial derivative with respect to the price of X here, we'd take the partial derivative with respect to Y. And then that would give us the, not the X star, but the Y star. Okay, so let's see if we can do that correctly, at least for X, and see how that works. So we have this equation, the 0.5428 times B divided by the price of X to the 0.3 times price of Y to the 0.7. Let me rewrite that a slightly different way, just to make it a little bit easier to see these derivatives. So let's rewrite it this way. 0.5428 times B times price of X to the negative 0.3 times the price of Y to the negative 0.7. Okay, that'll just make our life slightly simpler when we're taking these derivatives. So let's take this first partial derivative here. Take the derivative of this, U bar, with respect to the price of X. So what we're going to get is all these other terms will stay the same except for the one involving the price of X. So partial derivative with respect to the price of x is going to be 0.5428 times the price of y to the minus 0.7. And then what we're going to do is we're going to multiply by this exponent, so minus 0.3, and then we're going to take the price of x, and we're going to subtract 1 from that exponent. So that's going to be minus 1.3, okay? And let's clean that up. And what we should be able to get when we clean this expression up, what we're looking to do, oh, sorry, this is only part of it. My apologies. We also have to take the derivative with respect to the budget. So, and I also forgot to include the budget there. I told you I was tired. Okay. So this is just the first part of Roy's identity. The second part, what we're going to have to divide that by, so I'll put it directly below it, partial derivative with respect to the budget is very easy. Because we only have budget to the first power here. So 0.5428 times the price of y to the minus 0.7 times price of x to the minus 0.3. And Roy's identity says divide that first expression by the expression on the bottom, and you should end up with the same thing we had for x star up here. The x star equals 0.3b divided by the price of x. So let's just see if we can do that. So we're just going to want to start canceling a bunch of stuff here. So those 0.5428s cancel. Those price of y to the minus 0.7s cancel. So what we're going to be left with over here is a b in the numerator, minus 0.3, and a price of x to the minus 1.3, divided by price of x to the negative 0.3. Now, I can already see that I have probably messed up a negative sign somewhere. Let me see what I've done very quickly here. Okay, yeah, what I've done is, and this is typical for me, as I tell all my students, I am internationally known for losing minus signs. Roy's identity actually is this. It's that the Marshallian demand for x will be negative the partial derivative of utility with respect to x divided by the partial, that should be a curly d, partial derivative of utility with respect to the budget. And the reason why you have to put the minus sign here is because this derivative is always going to be negative, and so we have to cancel out that minus sign in order to get our Marshallian demand to be a positive expression. Why is this always going to be a negative sign? Well, because as the price of x goes up, we expect our utility to be going down, right? So that's why that's going to have a negative slope or a negative expression. So I should have put a minus sign over here, and that's going to cancel out that minus sign there, okay? And then you can see now how we're going to be able to get this to be equal to our x star that we had before, which was 0.3 times the budget over the price of x. Because those two, when you subtract the exponents, minus 1.3 minus a minus 0.3, you're going to end up with the price of x in the numerator raised to the minus 1 power, and that's the same as the price of x in the denominator. So that's how you can go from an indirect utility function back to get the Marshallian demands. And as I said, in order to go back to get the Marshallian demand for y, it's exactly the same idea, except you put the price of y in here. Now, I apologize for some of the little silly mistakes that I made, and I apologize for missing that minus sign. I told you I was tired when I started this. But hopefully, despite my mistakes, this has shown you some of the steps by hand that you can go through in order to do these derivations. If you catch any other mistakes or anything else I can do to make this clearer, please leave a comment in the comment section below or feel free to contact me with an email. Thanks and good luck in your economic studies, guys.